Hey students, I'm getting a lot of questions about series versus parallel, and rightfully so. You're kind of learning those, and it's sometimes difficult to tell whether two resistors are in series or are they in parallel, and I should say, or neither. And so there's got to be some process to kind of help you. And so let me put together a quick little video and see if this helps. I'll start with series. What does series mean? Well, as the name implies, series means it goes from one into the other, into the other, and the other. And because of conservation of charge, if the current's flowing, if it goes through one resistor, then all that same current has to go through the next resistor. So something would be in series if it looked like this. I'll just give it kind of a general power supply here. But if this is the first resistor, call it R1, and then, and the easiest one to draw is R2. Notice that everything that comes out of R1 has to flow into R2. So that's called series. Everything from this first one whoosh, goes right into the second one. And since they're drawn in a straight line, that one is kind of easy for students to visualize. However, you don't have to draw them in a straight line either. Here is another example of being in series. And they may not be in a straight line, but again, if you do conservation of charge, you'll see that everything comes out of here. It has no place to go other than to come along and make this downward turn and go into number 2. So everything that leaves number 1 goes into number 2. So again, we would call that series. Now, watch this one. This one probably gives students the hardest play because when you draw it, it looks like two parallel lines. And of course they are on the drawing, but when we say series and parallel in electronics, we don't mean the geometry of them. We don't mean you draw them in parallel. This is actually in series. This is really saying that all the current that comes out of resistor number 1, it makes this downward turn, then it makes a turn towards the left, and then it enters number 2. So everything that comes out of number 1 goes into number 2. So all of these are in series. So please, do not think they got to be drawn in a straight line. What they need to be drawn is with the idea that everything that leaves number 1 goes into number 2. Now, I can't imagine drawing anything quite this crazy. But if this is R1 and this is R2, those are in series because everything that comes out of number 1, and they have to kick a downward turn and a left turn and a downward turn and a right turn and a downward turn and a left turn and an upward turn, and it enters there. So everything that leaves number 1 goes into number 2. Kind of the easiest way for me to describe it is if there is not another connection, another wire. Well, we like to use the fancy word node. If there's not another node, by the time you draw from number 1 to number 2, then there's no place or no chance for current to either exit or enter. And therefore, the current coming out of number 1 goes into number 2. So I like to say, do this. If you're questioning if they're in series or parallel, just take your pencil or pen and right where it comes out of number 1, just trace along. It doesn't matter how many turns you make, how long you trace. But if you get to number 2 and there is no node along the way, so right here, no node, then it's got to be in series. There was no chance for the current to come in or to go out. So that's what happened here. I could draw straight across, no node. I can draw from here to here. Again, made a turn, but so what? No node. This one didn't have a node until I drew it. I went like that, and now I've added one here so there would be a node. So without this here, 1 and 2 are in series, but with this, 1 and 2 are not in series. And so this one, even though I'm drawing a lot of turns and a long distance, they're in series. So again, that's probably the easiest way I can explain to find if something is in series. Draw your little circuit, take your pencil or pen, and just draw from 1 to 2. or 2 to 3, 3 to 4, but draw from one element to the next. And if there aren't any wires or nodes sticking out along the way, then they're in series. And if there is, well, then they are not in series. However, be careful. You never, 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 never say if they're not in series, they must be parallel. Because we have series, we have parallel, and we have neither. And the neithers are more complicated ones. And so for this level of class, we don't usually get into the neithers of them. The farthest we get is having you write out Kirchhoff's laws, because those are the way to solve a circuit that has neither series nor parallel. But the easiest circuits are either series or parallel or some kind of combination, and we can do the equivalent circuitry. The ones that cannot be reduced to equivalency, we have to do the Kirchhoff's loop rules, and that's why part of this class is teaching you how to write out the equations, but we're stopping short of having you solve something like a system of equations that has 3 equations and 3 unknowns. In fact, earlier today I was doing a video on that we had this big loop to do, and it said just write out the loop. It didn't say actually solve it. And so that's kind of my description here. Now, let me move on to parallel. So, parallel, again, as the name implies, says that the current kind of splits off and can go either to the left or to the right, or either up or down. In other words, it has a different path. And so, like lanes on a freeway would be parallel lanes, because if you were traveling from city A to city B, you would get in maybe the slow lane or maybe the fast lane, but you don't do both. And as you look at the cars going down the freeway, some of them would be in the fast lane, getting to the city, and some of them would be in the slow lane, getting to the city. And so those are parallel lanes. You could actually have 2 separate roads. You could have like an old road and a new road. And so the old road goes to the city, but so does the new road. And some people are going to go the old road, and some of them are going to go the new road. Those are parallel paths. Nobody does both. You don't go down the old road and then circle around and come into the new road and go to the new road. You don't do both. It's not series. It's not one leads into the other. It's either one or the other. And some people do one direction and some people do the other. And so the same thing here with our electronics. And the easiest one to kind of see about parallel is something like this. Because our 2 resistors, R1 and R2, are physically drawn parallel. But like back here on the series, don't fall for the way they're drawn in the diagram. It's not about geometry. So, these look like in series and they're drawn in series, so they're easier to see. But like these, when this wasn't drawn, look in a drawing parallel, but they're electronically series. And this is the easiest one to see in parallel. Maybe another one easy to see in parallel is when it comes off and maybe you have it split. You got resistor 1 and then resistor 2, and then the circuit kind of finishes up. But you are physically drawing a picture where the lines are parallel and they are electronically in parallel. But again, don't fall for the trick that thinking they have to be drawn parallel to be electronically parallel. So why do we call this parallel? Well, the current comes out. And for the sake of discussion, let me just say this is 100 electrons per second. And they get to this little node and they split. And some of them go through number 1 and some of them go through number 2. And then they regroup. Okay? And then, just for the sake of discussion, let's say it's 30 going that way, which means 70 have to go the other way because of conservation of charge, right? They would split, right? 100 come in every second, 30 go this way every second, 70 go this way. But then they recombine right here. And so the 30 come in and the 70 come in, and we end up with 100 electrons each second, continuing on. But did you see you had two parallel paths? And so what you're saying here is these 30 electrons take one path, these 70 take another path. They both get from city A to city B. They each get there by a separate parallel path. And that's this idea of parallel. You can see the same thing here. It comes up, and then again, just for number's sake, maybe there's 100 every second. Some of them are going to take this upper path. Some of them are going to take this lower path. Maybe in this case, I'll make it a 60-40 split. Again, they all combine back together right here. And so there's 100 per second. But again, the 60 that go across the top do not go along the bottom. And the 40 that go along the bottom do not go along the top. They either do this path or they do that path. And so they're parallel paths. Some of you are getting your education at the university. Some of you are getting your education at the community college. You are both getting your education. You don't do both. You don't take physics at the community college and at the university. You either take it at one or the other. Some people take it at the university. Some people take it at the community college. So some people take this path. Some people take that path. They all started before taking physics, and then they all end up completing physics and then go on and do their other classes and their other things in life, go on and hopefully get their degree. But the point is there are two separate paths. They start at the same place, they come together, or they finish at the same place, and that's this idea of parallel. Now, that's why some paths that may not look parallel can be a little confusing. And here is probably the next step up. If I call this R1 and this R2, I look at my circuit diagram and I go, well, those don't look in parallel. Well, yeah, they're not drawn in parallel. So from geometry, they're not in parallel. But electronically, they are. Because if you think about 100 electrons coming out and they get right here, they now split. And maybe this time I'll do a 75-25 split. But the 75 that go this way end up at this point, and the 25 that go this way also end up at the same point. So all of them started at the same point and then went through their respective resistors and then regrouped right here. And that's the key. As long as they come back together, as long as they group back together, they've each started at one place and then got to the second place. It was just by a different parallel path. And that's how you would recognize if something is parallel. I don't know if this is much different, but maybe without drawing too many resistors. I'll put it here. And again, if I call this R1 and this R2, you can see that they get to this node and split. Some go this way and get over to here. But others go around this loop and go through number 2. And so this is parallel. And hopefully you're beginning to see like this very first one here, and this one here, and this one here are really the same thing. They really come up and they split. They each go through an R1 and an R2. And then they recombine and meet. So I like to kind of do this if it helps. It kind of helps to have a colored marker, 2 colors actually. Sometimes I'll just do kind of a little drawing. What I'll do is I'll say, okay, so let's say this is the place where they split, and I'll kind of draw those wires with metal, with one color, and say, okay, those metal pieces, these electrons go that way and hit resistor, and they hit that way. So in other words, I'll have, if you'll let me just say this, kind of a weird saying, I'll say I'll have red electrons going into resistor 1 and red electrons going into resistor 2. And then on the far end, I'll give them a different color, so I'll make them green. But over here, I'll give them a green. And then if I just keep drawing wires, then the greens meet up again. And so if the greens meet up, that means they left at the same place, red, and then regrouped here. Had there been another resistor here, in other words, had I had a circuit that looked like this, and so it's a little harder one. Call this R3. You can see that this little green drawing wouldn't have worked. I would have gotten to here and I would have hit another resistor and then probably have to have another color like blue, and then the blue comes together with the green coming down. So I guess it would look like this. Okay, so I draw red here, and then it comes out green here. And then maybe I say something like, well, this one comes out green here, thinking that maybe the green ones will match up like here, but they don't. They hit another resistor, which then that changes things to a different voltage, and so it has, this one has a different effect. It didn't just leave city A, although you might say the two of these combined are in parallel, and that's where I want to get with this. But right now I would say, oh no, these are not in parallel. By the way, they're also not in series. So they're kind of neither, at least for the moment. But I'm hoping what you did see when I was drawing this is that you could see that everything that left number 2 went into number 3. So you could, to solve this, do something like this. And say, well, 1 and 2 are not in series, but they're also not in parallel. And you might say at the moment they're neither. But you could say 2 and 3 are in series. So you might put the equivalent, and I'll put it as 2, 3. And in fact, if this had a resistance of 2 and this had a resistance of 3, since they're in series, we would add them and we would get a resistance of 5. So then once you draw this, you can see this one is looking a lot like here, where if you study this one, you would say, well, wait a minute, isn't that in parallel? And yes, because here's the red one, and it comes off like this, okay? And then when it comes through, it comes out green, and then they recombine. So then you could say those two are in parallel. And so then you can have the equivalent of the 1 combined with the 2, 3. And of course, if we give a value to R1, call it 1, we can then get the equivalent of these two by saying the reciprocals. And so 1 over the first one, so this is a 1, plus 1 over the second one, which is a 5, equals 1 over the equivalent, which is this 1, 2, 3, which I guess is a common denominator of 5. This would be 5 plus 1, which makes 6 over 5. So then when I do the reciprocals of each side, I get the resistance of 1, 2, and 3 equaling to 5/6. So I could say this is equal to 5 over 6. So that's how you would do a problem that was a bit more complicated and had more than 2 resistors. You might run into a case and say, you know, hey, these are not either series or parallel. So leave them alone and move on to something that maybe you can reduce. And so I like to say that this circuit is equivalent to this one, and this one is equivalent to that one. So you might call this last one the equivalency of the equivalent one. But of course, it's really nice to be working with a circuit that only has one resistor. And that's kind of the logic to them. But I guess I digressed a little bit from my original question. My original question is, how do I recognize if they are in series or parallel? And of course, I said, draw a straight line to recognize they're in series. Oops, sorry, I don't want to use the word straight. Draw a line. Doesn't have to be straight, doesn't have to be short, but if it just goes from one to the other without any nodes, it's series. And parallel, if they leave one and then recombine without going to another one, they're in parallel, which is why 1 and 2 did not work out for parallel. They're neither. But never, never fall into the trap by thinking, oh, if it's not series, it must be parallel. Or if it's not parallel, it must be series. No, it's series and parallel or neither. And so when you have something here that's neither, maybe you can get lucky and come over here and get something else that is in series. Then draw its equivalent. Then once you have its equivalent, maybe those are in parallel to get its equivalent. And so you actually can reduce it down to one resistor, even though originally you started off and said, oh, those two are neither series nor parallel. Sometimes you can't do that, though. And that's what I was saying earlier, that's a little beyond the scope of this class. We're going to do our circuits that when we run into something that's neither, somewhere else it is, and then we can reduce it all down. If we can't reduce it all down, we'll just tell you, hey, do a Kirchhoff's loop rule to write out the equation. And if you did that for all 3 loops, you would have something like 3 equations, 3 unknowns. And that's where the math gets a little longer, and we say that's good enough for this class. Well, hopefully that was helpful to someone. Take care.